Hello everyone, it's August the 10th. Alright, I thought about it. I really don't want to spend too much time on this every day. It's kind of messing up with the rest of the night. So I think I'll, instead of capping for 1 hour, let's capping for 45. Right? If we have an idea and then just keep flowing, then go for it. If not, I want to just end it about 45 minutes. Yeah, otherwise, it just this drags on and on. Kind of don't want that, especially at night. Dragging on and on is definitely not the way to go. I know myself. I know the performance and everything. These things drop as you get later and later. So, okay, so we will go into valid as an old problem. Given up to 2 if it's a valid. Only nodes with keys less than. The right nodes only keys greater than. Okay, so I think everything is unique. Oh, it's validating. Okay, so this is true. This is false because 4. Okay, yeah, I think nothing too bad with this. It's fine. It's always fine. Alright, so we're gonna validate. So I'm gonna say, I'm gonna validate is if not root. Oh, that's actually a good question. Number of nodes. It has to have left and right tree, right? Can we have only one? Like, for example, we say 2 and 1, right? Is this considered? So it's kind of, if it's no, do I return true or return false? It is true. So if not, we just return true. Otherwise, is left bst self dot is valid root dot left is right bst self dot is valid root dot right, and then return. Ooh. Is left is right, is left child good shall be root dot val shall be larger than root dot left dot val. It shall be if root dot left. How would you say this? If not, else is true. Like if doesn't have, as always. So we probably get this, right? And then we do the same thing. Say is right. Let's just say is left good. Is right good. The val must be smaller than right. The val. If the right. Once we're down, then return or is left good is right good is left bst is right bst. All of them has to be true in order for this to be true. Okay. The hell? That encounter a bug. Oh no, I just need to turn this off. Tree visualizer. Okay. Yep. December 16th. Oh, shoot. The heck? Expected false. Man. Come on, man. What the heck is this? What's this one? Oh. Oh. I forgot about that. Damn. Oh, we have to carry on. Man, oh man. Oh, I see. Another way we just traverse it, like pre-ordered traverse it, and to see if it's sorted. Ah, how would you do it this way? So if it's the left subtree, it should be smaller than that, right? So the right has to be smaller than that. So it's bigger than that, but smaller than that. So I have to pass a parent. I have to pass a parent val. So every time we check the left subtree, it's just smaller. It's straightforward. Oh no, it's actually not straightforward. It has to be bigger than the parent. No, it's grandparent. Oh, oof. Grandparent. Oh. What's the root of the grandparent? How can be a left subtree, right? This is left. If you're left, you have to be smaller than the grandparent, right? So I can do math.inf. And then we can have is left true. So the left subtree has to call root.left. Root.left, we check this, right? And then it's grandparent. But is a grandparent or parent's value? Oh, it's parent. It's not grandparent. It's just parent. It's just parent value. So parent value should be root.val. And then is left equals true. And this one, parent value is root.val. Is left equals false. Right? So you pass the parent value down. And then when you make the check, right? Then say root.val is left good. Root.val must be larger than this. Oh, have other checks. We say if is left, so we're on the left subtree. right? Then we say left good is, this is larger than this, right? And that should be it, right? The root value is larger than this, and then we know root value must be smaller than, because it's going to the left. Otherwise, it will error out. Okay, so nothing changed here, but this will change. Root value is smaller than this, right? If I'm on the left subtree, then we should be and root.right.val must be smaller than parent, right? Because root.right.val is on the left subtree, it must be smaller than parent. Okay, then we can say else. Then we are on the right subtree. Then the left must have and root.left.val must be bigger than parent. And on the right side is actually fine, because on the right side the root.val is bigger. So, okay, we are armed with a little bit more checks. Let's see if this is sufficient. Okay. Here's all the examples. Try this. What the heck? Wow. Okay, this is not the way to go. I don't think this is the way to go. It might work, but didn't work for me. Did not work for me. Alright, so 2 are wrong, so we have to find out a new way. The new way is array. It's a pre-order in order, which is a traverse node. Don't return anything. So what I think is we will go left, root right. And then we just traverse again to see if it's strictly increasing. Yeah, that's the check, strictly increasing. So we say if node traverse node.left, and then array.append node.val traverse node.right, and then for I in range 1, 2, line array, if array I is larger, smaller or equal to array I minus 1, then return false. Otherwise, return true. Okay, so we use this. That's completely different. I'm pretty sure you can do it the other way, but let me just pass it. Oh, a cow. What the hell? Found the second one. What? What went wrong? The traverse not right? Come on. Shoot. Oh. I forgot to call it. It's always like that. Not the first time I made this mistake. Array is not defined. Of course it's not. Alright, I believe this one shall work. Thank you. But still, why the tree method doesn't work? I mean, the runtime is the same, but the tree method would have done it without using extra space, right? This one requires extra space. Convert binary search tree to an and just traverse pre-order and then check whether the resulting array is strictly increasing. That's still ON. I'm curious what was the method I used in the past. I feel like they definitely increased the number of test cases. $80. 77. Yep, we can do a DFS. Wait, this is both DFS. Hold on, what the hell? So I say I make sure this pass. So I go in here, right? So in this one, I make sure this pass. But this must be the smallest. Huh. Like if you are on the right subtree, everything here on the right subtree needs to be bigger than this. So this should be the smallest value for everybody. Okay? If you're on the left subtree, then this should be the biggest value for everything. So when you check for this, you need to know the minimal value and the maximal value. So for example, in here, I know the maximum value. Alright? So when I check myself, if it's smaller, right? and then I check for whether my children. Oh, it's fine because a comment here. We have a smallest value. Everything should be bigger than this. Yes. But also the max value is here. A smallest value and a maximum value. Let's think again. So for each node, right, each subtree, how do I know this is, so let's say I know this is a binary BST, and I know this is a BST, right? Then I need to know the biggest value of this must be smaller than this, and the smallest value in this must be bigger than this. Oh, that now makes more sense. That makes more sense now. Check BST. We have a node. Oh, what do you return? I should return the max and then return the max and mean, right? The max value in this tree and the minimum value in this tree. So let's return three things. We'll return tuple, int, and boolean. Right. Int, and boolean. That doesn't sound right. What if it's and a none? What do none return? Oh, I can. Oh. No, like if along the way something is wrong, then I can just go wrong. So we say if not node, I just return. So this is the minimum on the left. On the minimum of this and the maximum of this. So I say max dot max, max dot not max, inf max dot inf and true, right? Otherwise, we say L min, L max is left BST equals check BST on the left, right min, right max, right BST, check on the right. If not this or not, then return 0, 0, false. Now we don't care, right? Otherwise, we should return. Oh, I should still current min shall equal to minimum of L. I think I can do this. L min, L min, R min, and no val. Current max, maximum, L max, R max, no val. Turn C min, current BST shall equal to L BST and R BST and the left max must be smaller, right, than no val. And right min must larger than no val. Then we just return. We don't need this. Just minimum, maximum, and then BST. Root. Let's try this one. Might work. Oh yeah. It's not working. Why? Wait, what is wrong with this one? Oh, we have a 119. Yeah, this is exactly as I was trying to do, right? I said when we check the left, we will get the minimum of this, which is 20. Maximum of this, which would be 110. And then say this one looks to be, yeah, this is larger than, these are all larger than this, these are all smaller than this. Yeah, this is good. Right? And the max is 110, this is smaller, okay? On the right side, we have this one. The min is 119. The max is 200. Right? So we say the right min must be larger than no doubt. This is false. Oh, I'm not returning the right thing. There we go. Let's add all the test cases. Actually, I think I can do this, this. Get all the test cases back. Yep. I think that is the stuff. There we go. Faster. Still ON, but a little bit faster. What method did I use in the past? Not this one. But I pass a min and a max. Same idea. So for each node, and I say min, my node must be, okay, then I check if it's a left node. So every one will have a min node and a max node. And then if we go to the left subtree, the max node change. If I go right tree, the min node change. Gotcha. This is actually better, huh? This one works. They all work. Alright, that'll be it for this one. Let's keep working on this. We need to do BIT. I kind of don't want to do BIT. I'll take BIT here. Oh, it's n plus 1. Okay, so BIT. Position delta I, where I is smaller than this. Self.bit I plus equal to delta I plus equal to I and minus I. I plus I and minus I. And this one is I was a range result. And the result plus, and then we have to change this if we want to do something else. I minus, okay, so we have the sec tree, which is handling the maximum, and we have BIT, which can handle the sum, right? So we have a sec tree, and we have a self.bit shall equal to BIT. What is the n? N is just n. And we have to also, we have to initialize the BIT. I say, how do we initialize the BIT? Well, I say for, because we have n rows. Oh, is that n rows? Yeah, we have n rows, and each has m, all right, initially. So we say for in range n, for I, this position, then self.bit dot update. Update and pass a position. Position is I. Delta. Delta is just m. Okay, this is initialization. Initialize both. So now we're gonna gather. So gather is k. So we have to do is binary search type of thing. We just want to know if it exists, right? Okay, so we can do this. Def, say search, gather, row. So to search, we need a low and a high, right? Low and high, and target, which is basically just k, and then we're going to return an int. So what do we search? How do we search? So we have a low and a high, so we get a mid. Shouldn't we say if Oh, are you doing recursion or are you doing? Yeah, well, I think I'm doing recursion. Nah, why recursion? We can do it while low is smaller than high, right? Mid is low plus high divided by 2. Then we're gonna say the left half, right? We say we're gonna query the maximum, so we say Lmax, right, equals self.segTree dot query. So segment tree query, just low and high will give me the maximum. So low and high. Inclusive, right? Low and mid include. So this is the left, and then right. Actually, we should check if left max is larger equal to target, right? Then we don't have to do the right. Then we just keep doing the left. How do we keep doing the left? We set high equals mid, right? Equals high equal to mid, because the left side we have higher than this. So high, we set this. Else, else right max equals self dot segTree dot query mid plus 1 to high, right? And we say if right max is larger equal to target, then low equals mid plus 1, right? So it'll go up. Else, so this is left is smaller, and then we're going to return minus 1, which means we fail. And then blah, 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 and then return low, because eventually we'll get to a value, right? And then low will equal to high. That's, I think, when we find it. Because eventually, when we get out, it has to be low plus 1. Because mid, wait, hold on. Mid, yeah, I think this is good. So this is search. So together, we need to first say index equals self dot search gather row. Low is 0, high is max row. Wait, is max row inclusive or not inclusive? Inclusive, I think. So target is k. Okay, so this will be index. So we say if index is smaller than 0, then when the return is not possible. Okay, otherwise it is possible, then the number of empty seats would change. I wonder if this is even needed. But anyway, so then we just say index will update to whatever the value. Oh, we need this value. This is the current. Now so we say self.empty seats index minus equal k. Right? So this is the current value. And then self.segtree.update. So segment tree update is index and the value. Okay, so index, what is my index is here. Value is self.empty seats. Index is the new value, right? And self.bit.update, right? Update query, position and delta. So position is index, delta is minus k, right? That's that. Okay, so that's gathered. And what do we return? Left 2, the row and seat number of the first seat being allocated. So row is going to be index. Seat number. We have m empty seats. So minus m minus this thing. So m minus self.empty seats index, right? So let's say we have, I don't know, we have 10 seats, 10 empty seats. We take one and say we take 5. Now we have 5 empty seats. And 10 minus 5 is 5. Oh, hold on. This is not right. We have m empty seats, right? The first return should be 0. Right? If we have, let's say, 5 is good, then it will be 5. If we have only 1 empty seats, and it's minus 1. Okay, so shall be RC equals index m. Don't even have m. Self.m minus self.empty seats index. That's the starting position. And then we do this, we do this, we do this, and then return R and C. Okay? That's the first one. Scatter. So scatter, we just need to find the total number of empty seats in the first max row. So total empty shall equal to self.bit.query. So query, we just need a max R, which is max row, right? So we say if total is smaller than k, then we return false. Can't see it, right? Return false. Otherwise, if it's larger than or equal to, holy guacamole, then for each one we need to, so for actually y I equals 0. So while k if self.empty seats I, if this one is larger or equal to k, right, then if this amount is larger or equal to k, then I take k and then call it a day. How do I take k? Well, we simply say self.empty seats I will be minus equal to k, right? And then we do this update sec_tree I self.this I. You know what? Let's call it index. Right? So if index of minus equal to k, this will be empty seats and update index minus k, right? And then k minus equal to k. And then we will come out. Else, well, k, well, it will definitely fit. So I don't need to check index. Else, this current one is smaller. Then we say self.empty seats temp equals self.empty seats index self.empty seats index will be a 0 and well, we'll do this all these things again. Update this, but this time that'll be 0. Right, that'll be 0. And then minus temp. And the k minus equal to temp. And then come out index plus equal 1. So come in this and then return true. 49 minutes. So we're gonna just submit this and not submit this. We check. Oh, out of range. Oh, I don't know what n plus 1. I forgot. That's the thing. I forgot what is the 2 to the. It's not enough. All right. Let's see. I hate this part. Let's say 1 to 5. So 1 to 3, 4 to 5, 1 to 2, 3 to 3, 4 to 4, 5 to 5, right? And then 1 to 1, 2 to 2. I need 1, 2, 3, 4, 5, 6, 7, 8, 9. But to finish everything, we have to say 10, 11, 12, 13, 14, 15. So 50. So for 5, 5 minus, it's n. That's our range. So range will be actually from 0. Now n is, so 0 to n minus 1. So yeah, it is n. So this is 2 to the 4th. Right, that's 2. Oh, that's on 2. 3, 5, my bad. So 1, 1, 2, 2, 3, 4, 5, 5, 3, 3, 4, 4. Doesn't change the result, but it's just slightly different. So we'll have divided by 2 will be 3. 2 divided by 2. So if we do log 5, we equal to 2, which gave me 1 layer and 2 layers. But 1, 2, 3, 4. I need 4 layers. 2 to the 4th. So we have 2 layers. It's 2 point something. So we do ceiling is already 3. And then 3 plus 1 is 4. 2 to the 4th. And is not enough? The heck? And this one's not even that big. N is 2. So all we have is 0 and 1. And 0, 0, 1, 1. So 1, 2, 3. And log 2 is 1. 1 plus 1 is 2. 4. This shall be more than enough. What the hell? So it's update, right? Update index. So I call gather first, right? So when I do gather, so max row is 0 and 0. I had already come out. Wait, hold on. That ain't right. I didn't even check. You give me a low, give me a high, right? So if they're the same, oh, actually we have to rewrite this. If they're the same, wait, gather is k and a max row, right? K and a max row, k and a max row. Max row is 1. Wait, hold on. Gather. If max row is equal to 0, that's a special case, right? So we shall just check it directly. Yeah. Oh, this will just directly return 0. If max row is equal to 0, that's a special case, right? Then we just checked 0 row. And then we say if it's equal to 0 and self.empty seats 0 is smaller than k, then return this. Done. Otherwise, we will call this is 0, but we won't do, and then we'll jump out 0, and then we'll do the rest, what is supposed to be done. So the gather, I'll add another one here. But still, I think we will still run into this issue. Let's just fix the first one. Yeah. We only have 2 rows, come on. Can I just see? I val this and j. If it doesn't, actually I can test it here. Why do I test it there? It's easier to test it here. Oh no, I have to call it. I'm not sure if I want to call it. Okay, 7. J is 7. 3, we have a 3. We have a 0. Value is 1. I is index. Huh? What the? Oh, what's after the first one? Then we have 1 empty seats. And then we're up to 0, 1. Oh, okay, I see. Okay, we have 0 and 1. So, in my mind, if I've that's a 0 to 1, that's a 0 to 0, that's a 0, 1 to 1. So we have 0 to 1, right? Not 0 to 1, we have 0, 1, and then we will enter with 0, 1, right? That's the first call. Perfect. And then oh shoot, I forgot to return. Dang it. I forgot to return. This one's right. Hold on, let me copy the whole thing. Now I'll need this one. And alright, if it doesn't work, we will check tomorrow. 1 hour. It's alright. It's not the best. Oof, I don't think this is right. Ooh, we timed out. What? What? We timed out. Holy crap. That's definitely not what I had in mind. We timed out. With binary search, segment tree, and binary index tree, and we still time out? Are you serious? So the logic is correct, but we timed out. It's segment tree. It is segment tree. What was the trick that was used last time to make segment tree pass? Holy crap, I forgot. I forgot what technique is used last time. Oh, it was another difficult question, and we used segment tree, and then we just kept timeout and we kept timeout, and eventually something. We used BIT. I remember that one. We eventually used BIT. But BIT, how do we handle maximum in BIT? I'm just curious. So I think this is correct. We just... Oh, wait, timeout on this one too. Holy crap. Huh. We have hints. I don't know. This is my first try, and then why do you think like is that some operations can be, I don't know, simplified? Oh, I remember. we need to keep track of who have been completely filled. Then we don't have to search from 0. Okay, that's something I can do. That's something I can do. You know what? Let's do this tomorrow. Yeah, this is definitely an upgrade, right? So if a row is empty, we don't have to try it anymore, right? Yeah. The update is always the more costly. The query is always faster. Okay. Okay. Yep. I know. This is something we can do. Hold on to this, boys. We will crack it tomorrow. Alright, I'll see you guys tomorrow. Adios.